How about let's chat about um, how we're uh, handling precision and repeatability and resolution.
Mm.
How we're how we're validating our solutions and providing specs for customers so they can have the correct resolution for their application.
Yeah. Resolution on the surface seems like a pretty simple, straightforward thing. You have a part, for instance, all of our parts, we have a 16-bit word that we output. So it could be easy to say, oh, we got 16 bits of resolution. But that's simply not the case for all of our sensors. In fact, we have some sensors that are 8-bit sensors. That means that 8 of those 16 bits, the 8 LSBs, are just noise. They're just, you get a free random number generator with them. It would be disingenuous of me to call those 16-bit resolution encoders because they're not. They have a 16-bit word, but only 8 real bits of information. And how we determine how many bits of real information we have for various parts. Again, we have parts that go from 8 bits up to that MA600, you can go to 14 and a half bits. How we determine, how do you get 14 and a half bits, for example? It's a bit is a bit, and you split it. And yeah, it's based on the noise of the sensor. So if you were to take the same exact measurement over and over thousands and thousands and thousands of times, you would get this spread of data, and it's going to be, if you did a histogram, it's going to be a nice Gaussian curve. And the idea is we want to know that if we took this, if we have this Gaussian curve and we move a little bit over here, what's the smallest amount that we can move and be 99.97%, I believe is what the number is. It's plus minus 3 sigma, that we are measuring this angle versus this angle. If you get too close and you've overlapped and now you're only 60% sure, we don't consider that. We consider that you're below the resolution of the sensor. We need to be 99.973 sigma, plus minus 3 sigma, sure that we've got 2 different angles, and that's what we consider resolution. And that goes back to, I think you can trace the roots of that back to A to D converters, and that's how AD converters were, how they determined what the resolution of the AD converter is. And it's a pretty conservative measurement. So if you look at our data sheets, and sometimes you compare them to some of our competitor data sheets, and you say, oh man, these guys say they're, this sensor is 12-bit. These guys have the similar sensor. They say it's 14-bit. What we found is that us and one of our competitors, and without naming competitors because I don't want to, I'm not trying to talk bad about anybody. Some of these guys I think are doing it on purpose, so-called specsmanship. Some of them, I think, just honestly feel that it's a fair way to represent resolution, but I'm pretty confident that our conservative method is the right way. So if you compare, we know of one other company that does it the way we do it, so kudos to them. But we know of companies that just say, hey, our output word is 18 bits of resolution, or that's very disingenuous. Some of them, they'll say, oh, our digital grid. Well, they don't even say it, but they know that their digital grid, their actual digital measuring grid, which you want to be very, very small, smaller than your noise, so you can actually see the spread of noise. They know what that is, and they say, oh, well, that's our resolution. And it's not, because yes, you have these little buckets, but your noise spreads out over multiple buckets. So you can't just use the size of the little bucket to say that's our resolution. So yeah, like everything, if you're comparing sensors head to head, you can't just look at the data sheet and take it at face value. You gotta test it. And the good news is, if you test the MPS sensors, you're going to see that we're quite conservative with our resolution measurements.
Yeah, it's good to know that we are plus or minus 3 standard deviations away.
Yeah.
And so with that information, you can know that you'll be able to, within 3 standard deviations, tell that there is a change in movement.
Actual change in the angle. Yeah.
Right.
Yeah, exactly.
Yeah, because it's independent of the word length of the amount of data.
Right.
Yeah,
Right.
like you were
I
saying.
could say, hey, we could just start putting out a 32-bit or a 50-bit output word. Now, 40 of those bits would be noise.
Right.
It's not a 50-bit sensor.
Yeah. Yeah,
Uh,
you could put a 50-bit word for your 8-bit sensor, right? And you could
yeah,
say
right, right. And then just say, oh, hey, look at that, 50 bits.
50-bit sensor, yeah, your
Pretty good
50-bit
stuff. Sell
resolution.
it for
Right.
$50. And, yeah.
Right. So well, anyways, I think that's a great example, great way to understand that for people. And so from do customers typically know what resolution they need, or is that something you have to often help people with?
It depends. It depends. So you have a lot of times you'll have a customer, and we tend to work with both an electrical engineer and a mechanical engineer because in order to get the correct field strength and the right linearity, the mechanical engineer has to place the sensor and the magnet in the correct orientation, and so we usually are involved with those two guys. And then there's usually a third party for at least for the applications that are like servo or feedback control. So again, like a robot. And that'll be some controls guy. And that guy will usually say, hey, look, here's the dynamic bandwidth that I need and the resolution I need to make my controller stable. And so when you have a guy like that, it's pretty nice. You have a definitive number, like here's the bandwidth, here's the resolution, here's the linearity. If we meet those numbers, we're good to go. Some customers, to be honest, just aren't sure. This might be their first time doing any kind of an encoder project. Not even they didn't use optical encoders in the past. This is the first time that they need to measure the angle of something, and they're not certain. And so in that case, we look at other. There's a plethora of different constraints that we look at to determine, okay, what resolution do we need? What linearity do we need? Do we even care about dynamic bandwidth? If something's going to rotate at some tens of RPMs, we don't care about bandwidth. But if it's, a turbocharger that's going to be at 80,000 RPM, all right, we got to make sure that our latency and our dynamic bandwidth is good. So that's our first concern. So yeah, it's a process to figure those out sometimes. It's a luxury
What's
when they have the number that they can just say,
they just say this will work. Yeah.
yeah.